Hi everyone. This series of videos is going to take you through lesson 8H, which is page 12 in the packet, and it's important to note that before you complete anything on this page, you do need to complete the Desmos activity. If you look in the learning plan, you'll find the class code as well as a direct link to the Desmos activity, but it is required that you do the Desmos activity before you do this packet page, which is a little bit out of order like we usually do. Usually I have you do the packet problems and then do the online assignment as kind of a follow-up, where in this case I think it's smart to go the other way around. Do the Desmos activity first and then do this packet page. The reason is twofold. First, because to answer some of the questions, it's going to ask you about some of the screens that you encountered. Like, for example, on number 1, it says on screen 22, which is referring to one of the screens in the Desmos activity. And second, because the Desmos activity is going to have you explore a bunch of stuff about these graphs, and it's through that exploration that you're going to make some observations and notice some things that are going to end up being helpful for this page. I'm going to talk about this page as if you've seen and practiced in the Desmos activity. So if some of these videos don't make sense, and it's because you've skipped ahead and skipped the Desmos, then you definitely need to go back, because otherwise this might be a waste. Now in question number 1, as I mentioned, it's referencing something that you found on screen 22. On screen 22, they gave you a formula, the general equation of an exponential curve that is located anywhere, not just the ones that we had seen in previous lessons that were at 0, 0, but the ones that could have a locator point anywhere. The general formula that you saw on screen 22 was y equals a times b to the power of x minus h plus k. Now, on screen 22, it didn't have parentheses around the b, but parentheses work if you want to put them. If you don't put them, it's no big deal. I just like to put them because we so often see parentheses in the equations, so it's kind of a nice compatibility. Now, that formula dictates several important things about our exponential graph. In general, the a value, or the number in the front, some of us call it the initial value, controls the y-intercept of our graph. I'm going to use that phrase y-intercept kind of lightly though, so kind of keep in mind as we're watching these videos, the phrase y-intercept will evolve a little bit, and I'll adjust this when we get there. The b still represents the multiplier of the sequence that we're dealing with, and h and k collectively represent what we call the locator point. Now the locator point is interesting in this one because the locator point isn't a vertex. It isn't even on the curve. And we've seen this happen before with hyperbolas as well. So if this kind of rang true to you and you're like, oh, wait a minute, I remember something kind of like this, hopefully it did remind you of familiar territory. Now, I think one of the best ways to make sense of a formula is to look at an example with the same structure and to try to figure out piece by piece the significance of each of these things. So I'll look at the example right next door and I'll see if I can make some matches. The a, for example, looks like it's in the same place as the 6, so I'm going to assume that's my y-intercept. The b is in the same spot as the 1/2, so that I can infer must be the multiplier. And now I'm looking at the h and the k. We recognized in the Desmos activity, as we've seen so many times before, that the h is always the one that does the opposite of what you'd think it would do. So if it says x minus 1, the x coordinate of the locator point is really positive 1, and the k coordinate keeps its own sign. So 3 would be the k coordinate, or the y coordinate. Now, if I go to my graph, 1, 3, so that's 1 and then 3 up, which is here. You noticed in the Desmos that this is not a point on the graph. That's not the point through which I draw a curve. That's the point through which we're essentially resetting the x and the y axes. So if you remember that idea that you were kind of dragging the axes around and resetting the axes at a new location based on the locator point, that's basically what the locator point is telling you. It's like, hey, draw a new X and Y axis over here. So if that's weird to you, remember we kind of did the same thing with hyperbolas. We used to draw an X and Y axis and then a box and all this stuff. The idea is pretty much the same here as well. So if this is familiar territory, hopefully you can tell yourself, oh yeah, I've seen this before. Another example of a place where we've seen this before was rational graphs. That was way back in chapter 5, because that was another situation where we reset the graph and then redrew it in its new location. In any case, now that we have this whole thing set up, we can look at the graph that we know, the y-intercept of 6 with a multiplier of 1/2 along the new axes. So I'm going to ignore the old X and Y axis and I'm going to focus on the new ones. On my new Y axis, my y-intercept is supposed to be 6. So 1, 2, 3, 4, 5, 6. Notice though that I'm counting my new y-intercept, or my new y-intercept off of the new y-axis, not the old one. That's the important thing to note. Now the 1/2 tells me that this is a decreasing exponential curve, because when the multiplier is less than 1, that's a decreasing exponential. So that's the kind that starts out tall on the left and then flattens as we go to the right. And notice where we flatten out. The flattening is against our new x-axis. That's always where the flattening happened before, but now we're flattening against the new x-axis, which is so important to notice. We're not using the old axes at all. We're totally ignoring them and using only the new ones. So now that I see where that flattening occurs, it's my new x-axis, so I want to look at that equation that's up 3 on the y, and you could say it's because it intersects the y-axis at 3. The equation of that asymptote then would be y equals 3. They will often ask you to write the equation of an asymptote, so it's relatively straightforward to do that. Just look at where the flattening of your graph appears to occur. Look at where your new x-axis is from your locator point, and it should all kind of communicate the same thing. So this in general is how you do what we call a translation of an exponential graph. This exponential graph had to be translated because of the h and k. So by shifting it to a new location and redrawing it, we're basically seeing the effects of h and k in action. H and k don't change the shape of the graph. It still does the flattening thing, but it definitely changes where the flattening occurs. And that's the most important part, is understanding where the flattening occurs and why. So in the next series of problems, we're basically just going to kind of keep practicing that relationship. If you feel like you don't quite understand it enough yet, I would definitely delve a little bit deeper into that Desmos. And if you still don't feel like you understand, even after having done the Desmos and watched this first video, pop into the Zoom office hours or simply email me with a question and I'll be glad to help.